So we're going to continue working a lot in coming weeks before the next exam on harmonic oscillators, including when we get to chapter 4, what are called forced harmonic oscillators, where it's not zero on the right-hand side, it's something non-zero. Here we're still in the realm of saying, okay, we like unforced harmonic oscillators, that's simpler. But we do want to think about bifurcations. So where do we start in thinking about bifurcations for something like this? We know that if the eigenvalues change from being real to complex or vice versa, that's a big change in what happens. So maybe we should figure out how the eigenvalues affect things. And that is also related to figuring out when we have underdamped versus overdamped. We know the characteristic equation can be written down without bothering to write any matrices. Just convert y double prime to lambda squared, convert b times y prime to b times lambda, convert 4y to just a plus 4. So the power of the lambda corresponds to the order of the derivative, second derivative there, first derivative, and 0th derivative. So there's a lambda to the 0 power, you might say there. And since we don't know what b is, we can't factor this. We've got to use the quadratic formula. Lambda is negative b plus or minus square root of b squared minus 4 times 1 times 4 over 2 times 1. Just a quick use of the quadratic formula there. Negative b plus or minus square root of b squared minus 16 over 2. Those will be the eigenvalues. And of course, you got to think about what's under the square root to decide if they're going to be real numbers or not. Real eigenvalues, if and only if b squared minus 16 is positive. So that's if and only if b squared is bigger than 16. Since b is positive, can't be negative, that's equivalent to b as being bigger than 4. If you allowed a negative amount of damping, negative friction, could you do such a thing? Well, sure, mathematically you could. Then this condition would hold even when b was less than negative 4. Question? Yeah, good point. Though I was kind of thinking about distinct eigenvalues. This is when you're going to have technically real distinct eigenvalues. If b squared minus 16 equals 0, if b equals 4, then you've got a real eigenvalue, but it's called a repeated eigenvalue. Because the thing under the square root is 0, you only get one real eigenvalue in that case, negative b over 2. And you might think that would be simpler to just get one real eigenvalue, but it's actually harder. When you've got a single repeated eigenvalue, we will see very shortly this week that it's harder to deal with. When you got real eigenvalues, that's when your phase plane has straight line solutions. We've seen it typically look something about like this. And the origin is a real sink, not spiral. I didn't draw that very well. Just a quick sketch. You're going to have complex eigenvalues. If and only if b squared minus 16 is less than 0, which ultimately means b is less than 4. And again, b is positive. And that's where you get spiraling. That's where you get what as we've seen with Euler's identity, cosines and sines become involved along with exponential decay. So you get spiraling. The complex eigenvalues are when b is relatively small, a small amount of damping, leading to oscillation. That's the underdamped case. Not much damping. And with the real eigenvalues, that's where you've got no oscillation. There's no cosine or sine involved in the solution. So this is the overdamped case. What's the boundary between overdamped and underdamped? That would be when b equals 4, and that would be that single real eigenvalue case. That has a name. It's called critically damped because it's the critical value between overdamped and underdamped. The critically damped case would never be observed in real life. But mathematically, it's still important because it's the boundary between overdamped and underdamped. effectively a bifurcation occurs. There's a bifurcation value at b equals 4, where we transition from underdamped to overdamped. Though, a little funny here, there's a species of mathematician called a topologist who would disagree with us on this, that that's a bifurcation value. Because to a topologist, they don't care about spiraling versus non-spiraling. All they care about is that it's a sink. A sink is a sink is a sink. I don't care if it spirals or not. I care. I mean, I like topology, but maybe I'm not a topologist. I care if it's a spiral sink or not. It does affect the picture. It does affect the physical situation. Is it oscillating or not? So to me, this is a bifurcation value, but a topologist wouldn't care. They'd say you got to have like a transition from a sink to a source or something to be a true bifurcation.